In quantum mechanics, if you constantly observe a particle, it seems like you should be able to freeze its state so it never changes. But that's not what happens, and what actually happens is even crazier. Observation itself can make time stop. Let me explain. It's me, and this is minute physics. Imagine a quantum particle that could be in two places at once. Say a particle of light called a photon that might be heading toward your face or over my shoulder here. I'll represent the photon's location possibilities with two switches, one for face and one for shoulder. Since the photon is in a superposition of states, we don't know which switch is on until we look. So let us say we flip both switches and then immediately check behind my shoulder to see if the photon is there. If it isn't, we know it must have gone to your face. This is the normal quantum measurement outcome. We learned something definite by making a measurement. But what would happen if instead of looking behind my shoulder, we flipped the switch back to the off position before checking? Well, because the photon was in a superposition of states at the beginning, it would seem that after we turn the switch off, it should still be in a superposition of states, still 50-50 chance of being on my shoulder or on your face. But that isn't what happens either. Instead, when we turn the switch off, the photon just disappears. It seems to have been destroyed by our observation. This sounds crazy. How could looking for the photon have destroyed the photon? That's the measurement problem in quantum mechanics, and we don't really know how to solve it. But I'm not going to try to solve it today. Instead, I'm going to focus on what happens next. So now we turn the switch off and the photon disappears. What happens if we turn the switch back on again? If the photon were still on its way to your face, then turning the switch back on should put it in a superposition again, a 50-50 chance of being on my shoulder or on your face. But since the photon disappeared when we turned the switch off, the only possibility is that it's on my shoulder. So turning the switch back on should put it in a definite state on my shoulder. And that's exactly what happens. The photon reappears. It seems that our active observation has frozen the state of the photon so that it doesn't change anymore. But this isn't quite right either. We don't actually freeze the state of the system. Instead, each time we repeat this process, the photon has a tiny bit less than a 50-50 chance of appearing on my shoulder. Each time we turn the switch off and back on again, the photon becomes slightly more localized on my shoulder and slightly less likely to go to your face. It seems as though every time we attempt to freeze the state of the quantum system, we succeed a little bit better than the last time. But this also means that each time we attempt to freeze the state of the system, the future possibilities of the system decrease. At the beginning, the photon had a 50% chance of going to either my shoulder or your face. But after the first round of switch flipping, the photon has a 50% chance of going to either my shoulder or your face. After the second round, it has a 25% chance of going to your face and a 75% chance of ending up on my shoulder. And after the third round, the photon has only an 8.75% chance of ending up on your face and a 91.5% chance of ending up on my shoulder. It seems like the act of observing the photon prevents it from having more and more future possibilities, but this isn't quite right either. A better way to think about what's happening is that every time we flip the switch off, we remove some of the photon's ability to be in a superposition of states. And this means that the more often we flip the switch off, the more massive the photon becomes. And sure enough, if we keep track of the mass of the photon as we play this game, we find that every time we flip the switch off and back on again, the photon gains a tiny bit of mass. By the end of the third round, the photon is more than twice as massive as it was at the beginning. This bizarre behavior is known as the Quantum Zeno Paradox. And just to clarify, it isn't a real paradox. It isn't a self-contradictory situation where both something and its opposite are true. Instead, it's just a name we've given to what appears to be a confusing set of behaviors. But the Quantum Zeno Paradox does highlight some important points about quantum mechanics. First, quantum particles don't have definite properties until they're measured. The photon doesn't have a definite location until we check. Second, even after a quantum particle is measured, it doesn't stay in whatever state we found it to be in unless we stop observing it. Third, in some sense, observation makes the future less likely to happen. Or, to put it positively, observation makes the present more likely to happen. Observation makes the future less likely to happen. What do I mean by this? Well, when we repeatedly measure the photon, we remove its ability to be in a superposition of states. And this makes it more likely that we lines find it in the same place next time we measure it. In this way, observation makes the present moment more likely to happen while making the future less likely to happen. And this brings us to the most bizarre part of the Quantum Zeno Paradox. When we make the photon massive enough, we remove its ability to move. In other words, we freeze time. In order to make the photon massive enough, we need to flip the switch off and on again a lot of times. And the more times we flip the switch, the more massive the photon becomes. But eventually, the photon will become massive enough that we can't flip the switch off and on again fast enough to keep it on my shoulder. Eventually, the photon will become so massive that time itself will pass too slowly for it to escape my shoulder. In this way, observation itself can make time stop. Now, the photon isn't really massive. What's really happening is that we're remaking the photon less and less likely to be in a superposition of states, which removes its ability to move. But regardless of whether the photon is literally getting massive, the result is the same. By making the photon massive enough, we can make time slow down until it effectively stops. I know all of this sounds kind of made up. You might be thinking that a photon can't possibly get massive enough to stop time, but you'd be wrong. Even a tiny increase in mass is enough to stop time. For example, if the photon were only 10 times more massive, time would slow down by a factor of 10. And if it were 1 trillion times more massive, time would slow down by 1 trillion. Now that might sound really hard to achieve, but photons can easily be made 100 trillion times more massive. Making a quantum particle massive enough to stop time isn't all that hard. And although it's really hard to make a photon massive enough to stop time in our everyday reference frame, it's easy to imagine a universe in which a photon is massive enough to stop time. In our universe, the speed of light is about 300,000 times faster than the speed of sound. But if gravity were stronger, the photon would experience a greater acceleration due to the gravitational pull of matter, which would make it more massive. In fact, if gravity were strong enough, light couldn't escape the surface of a star, stars wouldn't shine, and life as we know it wouldn't exist. But if gravity were only a little bit stronger, the speed of light would be only a tiny bit slower than the speed of sound. And under these conditions, a photon could get massive enough to stop time. In other words, under the right conditions, time could really stand still. So the next time you're standing next to a really cute girl, remember that if time stood still, you'd be the coolest guy in the room. If you'd like to learn more about the math behind all this, I've added some resources to the description. Also, you can watch this video I did about Schrödinger's cat, which is another famous thought experiment in quantum mechanics. I'd also like to thank my supporters who helped support this channel. I put your names in the credits as soon as I figure out how to add them to this new format. As a small token of my love and appreciation, I'll give you a digital copy of this adorable picture of a Shiba Inu. Thanks for watching. See you next time.